Hi everyone, let's start section 2 of chapter 6, queuing models. This section will be recorded in two parts, so this is the first part. In section 2 of chapter 6, we'll have the steady state behavior of queuing models. So in this section, we'll consider several standard queuing models and we'll see how we can obtain their performance measures like the average number of people in the system or the average waiting time in line, for example, if we assume that we are in a steady state behavior. So let's see what do we mean by steady state behavior. So what's the steady state behavior of a queuing system? We'll say that a queuing system is in steady state behavior if the probability that the system is in a given state is not time dependent. For example, if we are going to compute the probability of having n customers in the system, this probability should be independent of the time. So when we have this situation, if you remember in a simulation that we had in chapters 2 and 3, for example, when we run the simulation model for, let's say, 100 runs for 100 new arrivals, for example, and then we calculate the performance measures. Anytime that we run this model for 100 new customers, we will see different values for the performance measures, right? You remember that, right? But if you remember, when we increase the number of runs, let's say from 100 to 1,000, or when we replicate the simulation model for 500 times, 1,000 times, then we obtain more stable results, right? So we call those stable results as the steady state behavior of the system. So here we mean that we are running the system for a very long time. Then we have a large number of data for the arrivals, for the departures, for the services, and so on. Then we calculate the performance measures, the averages, by considering that large amount of data. So the results would be stable enough, right? So this is actually called the steady state behavior. So here we are assuming that we are operating the queuing system for a very long time, and then based on that period, that long time period, we calculate the performance measures, and then we call that as the steady state behavior of the queuing system. Okay, so here we're going to consider Markovian models. In Markovian models, we assume that the arrivals follow a Poisson process with rate lambda. Okay, so in Poisson process, when we call that, we assume that the rate is lambda arrivals per time unit. For example, let's say 10 customers per hour. So here we assume that our time unit is 1 hour or 60 minutes, and then we'll have 10 customers each hour. Okay, so when we have Poisson process, it's equivalent to say that the inter-arrival times are exponentially distributed with mean of 1 over lambda. So when the rate is lambda, then the average time, I mean average inter-arrival time is 1 over lambda. Okay, and the service time could be exponentially distributed. If it is, we call this as m in the notation of representing the queuing models, or it could be a general distribution. Okay, and the Q discipline here, we assume that is FIFO, first in, first out. And so here, since we are assuming exponential distribution for arrival process, I mean the inter-arrival time in arrival process, because of that, these models are called Markovian models. So anytime that we have Markovian models, we mean that the inter-arrival time between arrivals is exponentially distributed. Okay. The results that we obtain here in steady state behavior of the systems are not appropriate for the transient behavior, I mean the behavior of the system in short term. But If we are interested to analyze a system in short term for transient behavior, then we may use the mathematical models developed for transient behavior, or we can use simulation. Okay, so here we have some standard models, and each model has its own assumptions. Okay, so assume that we have an actual system, and none of the mathematical models fit exactly to this actual system. But we can find one of these models as so close to the actual system, then the results obtained by this mathematical model can be a good estimation, an approximate result for that actual system. But if a mathematical model is applicable, I mean, all the assumptions are hold in the actual system, so one of these models is a good fit for that actual system, then the results obtained by the steady state behavior of these models, I mean this model, not this model, will be the true value of the results in the actual system. And here the results obtained by the simulation would be estimate of this true value. Okay, but for more complex systems, when we can't find any of these standard models to fit to that more complex system, then we have no way to go with simulation, right? Yeah, I mean, even assuming one of these models wouldn't be, I mean, good enough in order to have a good approximation. So in that case, we have no way to go with just simulation. Okay. For the simple models that we have in this chapter, we assume that L is calculated by this equation. So L is the average number of people in the system in long term. So here N is the number of people in the system, and Pn is its probability, right? So we are multiplying each number with its probability, and then we are summing all the numbers, so that will be the average, right? The true average of the numbers in the system. So this is, it could be a performance measure for the system in long term, so in long run measure for systems performance. Okay, so if we calculate L by this equation, then we can calculate other measures by the Little's rule, right? So yeah, by having L and lambda, if you remember, the lambda is the parameter of the queuing model, I mean the arrival rate. So so W will be L over lambda, so we will have the average waiting time in the system, or WQ, the average waiting time in the queue, will be W average time in the system minus 1 over mu. Okay, so here mu is the service rate. Okay, or LQ is lambda times WQ, or it's L minus lambda over mu. Okay, so let's have the first standard queuing model. So here we assume that the queuing model is MG1. So the arrival is based on Poisson process. The interarrival time is exponentially distributed, and G means the service time is in general distribution. It could be exponential or any other distribution, and one mentions that we have just one server, so it's single server. Okay, with the unlimited capacity, so the capacity is unlimited here. Okay, so yeah, here we assume that the Poisson arrival rate is lambda, the service time is general, but we know that it's mean service time is 1 over mu, and its variance is sigma square. Okay, so here we assume that we should actually assume this assumption, because without this assumption, the system wouldn't be stable. So rho, I mean lambda over mu, the utilization rate for the server should be less than 1. Okay, so yeah, by having these assumptions and this model here, we can calculate the performance measures by these formulas. Okay, so if you see here all the formulas are based on the parameters. I mean the model parameters. Here we just assume that we have the lambda, we have the mu. Lambda is the arrival rate, mu is the service rate, and also we have the sigma, standard deviation, or the variance. Okay, so yeah, I mean here we have the formulas here, and P0, the probability of having no customer in the system will be 1 minus rho in long term. Okay, so I will provide you with Excel file, and in that Excel file, in that Excel file, we will have all the models with their formulas. So in any example or problem that you want to calculate the measures, you just need to enter the parameters value over there, and then that Excel file will calculate all these measures for you. So you don't need to implement these formulas in Excel, because I will provide you with that Excel file. So you just need to understand here that we have several standard models, and each model has its own formulas to obtain the performance measures, and that's it. Okay. So let's have an example here for MG1Q. Customers arrive at the walk-in shoe repair shop at random with Poisson process at rate lambda equals 1.5 per hour. Okay, and shoe repair times follows a general distribution with fx here. So here, as you see here, we have the x as the service time, let's say in minutes, and we have their probability. So here, actually, this is the probability of x equals little x. Okay, so we're interested in calculating the L, the average number of shoes in the system. Okay, so as you remember, we need to have 3 parameters in order to use the formulas for performance measures. The parameters are lambda, the arrival rate, mu, the service rate, and the variance. Okay, the variance of the service. Okay, so here, as you see, we have the lambda, but we don't have the mu, right? But we do have the distribution of the service time, so we need to calculate mu and sigma square first, and then go with the formula for L. Okay, so the expected value of the service time can be calculated by this, since it's a discrete distribution. So we need to sum up over the x values for x times its probability. Okay, so here we have the first x is 10 minutes times its probability 0.1 plus the second one 20 minutes times 0.3 plus, and so on, up to 50 times 0.1. Okay, so if we calculate this expected value, we reach to 30. So this means that the average service time, I mean the average shoe repair time, is 30 minutes. Okay, so for mu is the rate, right? That's the time, the 30 minutes. So it's in the minutes, right? But our time unit here is hour, as you see here, per hour. So the 1 over mu, I mean the mean service time, is 0.5 hour. Then mu will be 2, right? Mu will be so the service rate will be 2 per hour. Okay, and for the variance, as you remember, sigma s square is this expected value of x square minus expected value to the power of 2. right? So yeah, we do have the expected value, but we need to calculate the expected value for x squared. So here you need to actually obtain the x squares. So it will be here 100, 400, 900, and 1600, and 2500, right? And then so you have the x squared. Again, you have the probabilities, so you can calculate the ex squared like the ex. You just need to multiply the x2 values by the probabilities right here, and then add up the numbers. You can obtain the ex2. So if you do so, and then subtract that value with from uh, ex to the power of 2, you can obtain the variance or sigma score as 140. Okay, and so as you see here, the lambda is 1.5. The lambda, right? Lambda is 1.5. The mu is 2. So the rho will be 1.5 divided by 2. So now we have all the parameters, and we can go with the formula. So as you see here, for this formula, we have all the parameters. So we can obtain the value of L easily in Excel. So yeah, I mean, in Excel we don't need to implement this formula directly in Excel, because we do have that Excel file. So we just need to have these parameter values and enter these values in that Excel sheet, and then we will have the value for L and other performance measures as well. Okay. The second standard model that we assume here is MM1. So MM1 means that the arrival is based on Poisson process. So inter-arrival time is based on exponential distribution, and also the service time is also based on exponential distribution, and we have one server, single server. Okay, so here we assume that the inter-arrival time is exponential with mean of 1 over lambda, and also the service time is exponential with mean of 1 over mu. So these are based on the time, but the rate will be lambda and mu. Okay, so the rho is lambda over mu. So here we have again the formulas for MM1 queuing model. Okay, and yeah, I mean, that's again easy. You just need to obtain the parameters and then go with these formulas in order to obtain the performance measures. Okay. So here we have two examples for MM1Q. The first one is about a hairstyling shop, and we have the lambda as 2 per hour, and mu, the service rate, as 3 per hour. So we have the lambda and mu, so we can easily calculate the rho here. The utilization rate will be lambda over mu, so it's 2 divided by 3, so it will be this, right? So now we have lambda, mu, and rho, so we can easily use the formulas in order to obtain the L, W, LQ, and WQ, right? So, and for these probabilities, in order to, probabilities of having 0, 1, 2, 3, or 4 or more than 4 customers in the system. So we know that the Pn equals 1 minus rho times rho to the power of n, right? So P0 will be 1 minus rho, right? P1 will be 1 minus rho times rho. P2 will be 1 minus rho times rho to the power of 2, and P3 will be 1 minus rho to the power times rho to the power of 3. So for P4 or more, so here we assume that the probability of n be greater than or equal to 4, right? So it's equal to this 1 minus p n less than 4, right? So it's equal to, again, 1 minus p n less than or equal to 3. So it will be 1 minus p0 minus p1 minus p2 minus p3, right? So we do have the values for p0 here, p0, p1, p2, and p3. So we can easily calculate this equation, so we can obtain the probability of having 4 or more customers in the system by this, right? And the second example that we have here is 6.11 from the textbook, and here we have the mu as the service rate as 10 customers per hour, and the lambda here, at first we assume that it's 5 customers per hour. So here 5 over 10 for the base one. This means that the utilization rate will be 0.5. I mean, half of the time the server will be idle, or half of the time the server will be busy, right? So here we would like to increase the lambda from 5 to 8.64 by the increment of 20% each time, or up to 10. I mean, we will increase the lambda from 5 to 10 actually. And for any number, we can calculate the L and W, and then we can provide here a curve by having the values and the numbers based on the formulas. So we'll see how L and W are increasing based on the increases in lambda. Okay, so yeah, we can easily calculate the values and have the curve in Excel by having the formulas that we have in that Excel file. Okay, so this was the first part. In the second part, we'll see more queuing models. Okay, thank you.